Okay, so continuing on with some of our practice here for significant figures. This next example this is a little more realistic to some of the issues we might see doing a chemistry calculation. And one of the issues we need to worry about here is that we're switching. We start with a division, but then we're going to do a subtraction. And what we want to be really careful about is not rounding every time that we do an operation. We only want to round once at the end of the problem. Sometimes that's going to require you to kind of keep track of where your last significant digit is, and I think this is a good example of that. So if we just start with the division inside the parentheses, this is a 5 significant figure number, 6,104.5. We're dividing by a 2 significant figure number, which is 2.3. And the answer we get in the parentheses here is 2,654.130435. That's to the end of my calculator screen. But what we need to realize here is that that should be our last significant figure right there, where the 6 is. Now, we don't want to round, particularly if you're going to multiply again. Rounding could introduce error after error after error as you go through a calculation. In this case, what we need to keep track of is that's the last digit we should report any significance in. So when I subtract here, I'm going to be limited to the hundredths place in my answer. So if I go ahead and do this subtraction, 320.5 minus, and then I'm just going to pull up my previous answer on my calculator. My calculator gives me negative 2,333.63043.5. But again, based on subtraction rules, I've got to stop here in the hundreds place in my answer. So I can keep the 2, but that 3 there in the hundreds place is the last number I can record a significant figure in. So the answer here should be rounded to minus 2,300. And I add zeros that are not significant figures to maintain the value of the places where the 2 and the 3 exist. So you can't just leave off those zeros and change it to minus 23. That's a lot different than minus 2,300. But that's what you're going to want to do when we do a more complicated calculation, is just you got to keep track along the way, either what place am I worried about or what total number of significant figures am I worried about, and then round only when you get to your final answer. Now, the last one here is a little more straightforward. 2 multiplications in the parentheses. That's a 2 significant figure number. So this first parentheses will be limited to 2 significant figures. And that comes out to be 90. Now, 90 with 2 significant figures, we'd add the decimal right there. But the second number here, the second multiplication, is also 2 significant figures. And that's going to really kind of do away with the 90. So 33,756. But again, if this is 2 significant figures, maybe a little mark like that to let us know our last significant figure is really there. We should be rounding to that place. So when I add these together, 33,756 plus 90, what I get is 33,846. But if I have to round to that place, which I do, that means I round this to 34,000. And that should be my final answer for the problem. Okay, we will see lots and lots of significant figures every time we do a problem. That's something you should think about, is how many significant figures are in the data I'm using, and how might that change based on the mathematical operation that I'm using. One more kind of math-related issue we want to look at is called scientific notation. So what we'll see in chemistry are really large numbers and really small numbers, often with up to 20 to 30 zeros involved, right after the significant figures if it's a big number, before we get to the significant figures if it's a small number. So what we need is a really convenient way to express big and small numbers without having to maybe count out all those zeros that we need to write in between. Now, the way we're going to do that, we're going to take what's considered a standard number or a standard notation number, we're going to separate it into 2 pieces. One piece is going to be the coefficient, and that's only going to be the parts of that original number that are significant. Right? And another thing that would be worth saying in here, we want the coefficient to be between 1 and 10, right? But not quite 10. If it was 10, we'd just move the decimal and make it 1. So coefficient should be between 1 and 9.99999. Right? And then the other piece of information will be an exponent. And the exponent expresses how far the decimal moved from our original number to make the coefficient. And I'd like to show how this works here with a couple of examples, right? Ones that are maybe a little easier to figure out. 64 million, right? If I just take the significant parts here, that would be the 6 and the 4. And what I want to do is move the decimal in between the 6 and the 4. That gives me that value between 1 and 10. That would be my coefficient. I'm going to multiply the coefficient by 10. And then I'm going to use an exponent to describe how many times I'm multiplying by 10. So if I take 6.4, the decimal is between the 6 and the 4, I'd have to multiply 6.4 by 10 1, 2, 3, 4, 5, 6, 7 times in order to move the decimal where it was in the original number to where it was in the original number. So if the decimal was here and it ends up there between the 6 and the 4, that's 1, 2, 3, 4, 5, 6, 7 places. So I'm moving it 7 places either way, from the standard number to the coefficient, or from the coefficient to the standard number. And then the exponent is describing how many places I might have moved it. This works for small numbers as well. The non-zero parts here are the 5 and the 7. So to make that between 1 and 10, I'll make it 5.7. Right? And again, the formula is always times 10, although in this case, we'd be taking the 5.7 and basically dividing by 10. And we'd need to do it 1, 2, 3, 4, 5 times. So to express that we're dividing, we just put a negative in front of the exponent. So 5.7 times 10 to the negative fifth is basically the same as 5.7 divided by 10 5 times. Right? Divide by 10, divide by 10, divide by 10, divide by 10. Each time is going to move the decimal one more place. Right? Now you do have to watch out for zeros when you're doing scientific notation. 2300.0, that's a 5 significant figure number. And that means when we make a coefficient out of it, it should also have 5 significant figures. So we can add extra zeros there to make sure we still express the same number of significant figures, and the decimal would have had to move 3 places here. So to get the same number, right, expressing the same information, we need to add those zeros into the coefficient so that it's still a 5 significant figure number. Right, just to be clear here, we can do this in the opposite direction as well. If I take 3.5 as a coefficient, but I multiply by 10 6 times, that would move the decimal 1, 2, 3, 4, 5, 6 places. So there would be that many zeros. So that would be 3,500,000. And same for a small number, 4.78. Multiplied by 10 to the minus fifth, that would mean I move the decimal 5 places. 1, 2, 3, 4, 5. Right, that's where the decimal would be, so there would be 4 zeros in between the decimal and the significant parts of the number, or 0.00000478. Scientific notation works in calculations the same way we described. 6.21, that's a 3 significant figure number. 0.1050 is a 4 significant figure number. So if I do that multiplication, I want a 3 significant figure answer. So 6.21 times 10 to the third times 0.1050 is 652.05. Right? But since I can only keep 3 significant figures, I can keep the 6, the 5, and the 2, but I'm going to drop everything else. So that should just be 652. Right? Or if you did want to put it into scientific notation, 6.52 times 10 to the second. Right? Same number, so it's describing all the same information. So it's not like one's right and one's wrong. They're both describing exactly the same thing. Now, scientific notation does give us some flexibility to express numbers that can't be expressed in standard notation, and that's what this last example is. If you take 30, right, notice it's a 3 significant figure 30, multiply by 100, also a 3 significant figure 100 with a decimal in there. 30 times 100 is 3,000. Well, you can't really write 3,000 with 3 significant figures, in standard notation, because if you don't put in the decimal, it's one significant figure. If you put in the decimal, it's four significant figures. So the only way to write it with three significant figures is to use scientific notation, because the coefficient could be 3.00, and then you multiply that by 10 to the third, that would be three significant figures. So that would be the correct answer to this problem, and you can't really express it correctly using standard notation. Now, you could also do two significant figures using scientific notation. If you just take 1 0 away from the coefficient, you also get a two significant figure way to write the number 3,000. Okay, that's it for the math issues. The other part of chapter 1 will delve into units and problem solving and start to talk about density. But look to the next video for that.